Wearable interfaces have been utilized for XR interactions with their advantages in ergonomic comfort, compact form factors, multimodal sensing capabilities, and personalized haptic feedback availability. We believe that the adoption of wearable interfaces has the potential to advance interactions in XR by supporting more personalized and realistic experiences. Human-Centered Interactive Technologies Lab at KAIST is a multidisciplinary research group exploring novel interactions for XR through sensing and haptic feedback technology. We present demonstrations from recently published works and work-in-progress projects from 3 research areas focused on enhancing the XR interactions with wearable interfaces. These include adaptive input with multimodal wearables, hand interactions using multimodal wearables, and immersive experience with body-based haptic rendering. Now let's start by demonstrating adaptive XR input with multimodal wearables. Pointing is a primary interaction in AR/VR that allows users to manipulate user interfaces and virtual objects. In this demonstration, we focus on pointing interaction facilitated by wrist motion angles using a wrist-worn device instead of controllers. Unlike pinch raycasting, this method allows continuous estimation of raycasting independent of the H&D tracking system. In this demonstration, we present an EMG-based sensing technique to estimate the force transmitted by the user's hand when interacting in different hand postures. After training with multimodal sensing data, it will visualize the 3D hand posture and the pressure distribution heat map in real time. In this interactivity, we present Haptic Pilot, which is an in-situ haptic experience designed for hand wearables and VR. We applied our posture adaptive haptic rendering algorithm with a novel haptic design abstraction called the Phantom Grid. As an authoring tool, our toolkit provides a consistent haptic experience across different hand postures. To provide an immersive and realistic haptic experience when interacting with virtual objects, we have developed a multi-joint kinesthetic feedback glove from an electrostatic clutch to enhance object shape perception. With our haptic rendering algorithm, users can better perceive objects with different numbers of edges and sizes. Thermal feedback is an essential haptic feedback to provide an immersive VR experience to the users. We use 2 sensory illusions, vibrotactile phantom sensation and thermal referral for thermal rendering. We aim to reduce the burden of hardware and make the thermal sensation dynamic. By integrating them, the glove can render the thermal sensation and its movement. In this demo, by using only Peltier modules and LRA mortars, we showcase dynamic thermal rendering on a haptic glove, where participants are able to interact with virtual thermal objects in real time. We introduce HapMotion, a novel haptic rendering framework that translates the performer's motions into vibrotactile feedback for an immersive VR dance performance. We propose a motion salient triangle that aims to effectively translate characteristics of movements into vibrotactile haptic feedback. In this interactivity, participants will experience our HapMotion framework by wearing our customized haptic suit. The cause of VR sickness is a sensory mismatch between what the user sees in the virtual and feels in reality. To close this gap, we mimic the perception of neck rotation through neck muscle vibration. In the demo, experience the effect of neck muscle vibration on VR sickness.